My name is Dušan. As you said, I'm one of the authors on this paper, and besides me, there are Milena, Milošević, Marija, Antic, and Nikola Teslic. I'm presenting one more automotive-related topic to you, and this is one way of handling deterministic scheduling on GPU as the most used hardware architecture in automotive for different kinds of deployment of different automotive algorithms, of course. And the usage of, just a second to see if, am I changing the slides right now? Yeah, okay.
Yes.
The usage of the GPU as an effective accelerator for a really wide range of applications in automotive basically become a global trend. And I just want to point out at the beginning that this does not mean that basically GPU utilization will make other hardware architectures inapplicable. Uh, for example, DSP is even better in processing the initial sensor data. Some kinds of CPU are even better in planning and action related stuff, but GPU is certainly the best for environmental perception. So basically, the hybrid architecture seems like a fair solution, but on this paper, the accent is only on utilization of GPU. And basically, the main setback for utilization of GPU in automotive is non-determinism. Why non-determinism? Keeping in mind that everything we are considering in automotive needs to be available in real time. So real time execution is kind of must in automotive. Basically, determinism is a key challenge we will need to overcome. So we can have developing, debugging, and even testing more easier for implementations and uh, for execution. And basically, one segment of deterministic execution that we examine through the paper is deterministic scheduling. And because I already say the types of applications in automotive are really have a wide range. They all differ in terms of priority, criticality, uh, etc. So basically, we will have to implement uh, four different types of requests. EAT, which is based on the exact activation time, EDF, which is based on deadline, basically, and priority based and simple first in, first out uh, type of request. And those four names are in the same time the names for queues for corresponding queues which are handling the corresponding types of requests. We simulated basically behavior where software component uh, sending request to our manager and in order, of course, for their task to be executed. And once the request arrives, uh, the manager will dispatch uh, that request to corresponding queue. Uh, we we tried to implement two approaches: fixed priority and dynamic priority as well. And for each of them, we implement two different types of queues. First is a fixed priority queue. It is a queue which actually sort the requests based on their priority level, a value assigned by the software component. It is time independent, so basically it means that in any point of time, if hardware is available, of course, some request from this queue can be dispatched and executed. And basically the second fixed priority queue is implement for lower priority requests. Uh, Basically, it doesn't have any specific priority tag, and it is of course again time independent because it's fixed priority queue for fixed priority utilization. Then first dynamic priority queue, which is implemented, is EDF. It is, of course, time constrained because it sorts requests based on a deadline. The ones closest to the deadline will be considered first for the execution. The second dynamic priority queue is EAT queue. The requests in this queue actually have a predefined times of execution, and they have a highest overall priority, which means that in their time slots, no other requests and tasks shall be even considered. Okay, the process of scheduling of the requests is depicted on this slide. And firstly, we need to check if our queue with the highest overall priority, EAT queue, is empty or not. If it is not empty, we examine the top request activation time. If we confirm that activation time matches the current time, it goes straight to the execution. And if not, it will go back to the first step if the activation time actually passed the current time. Error will be recorded and the top request will be popped out from the queue. And if it is not the case, if there is still more available free time, the program will go to step 1.2 to see if that free available time can be utilized better. Then we need to check EDF duration. Basically, if there are no requests in EDF queue or their duration is longer than available time, the program will go to the step 1.4. And if it is not the case, the program will go to the step 1.3, where we only need to check if top request from EDF actually actually can be executed before its own deadline. Then for step 1.4, we only need to check if requests from priority queue, if there are any, of course, can be executed before EDF and EAT request. If yes, program will go to execution, and if no, program will go to the step 1.5, where actually the same scenario is repeated, but this time for first in, first out queue. And steps 2, 3, and 4 are basically the same as step 1, only checking if those queues are empty, but of course, all of them are for a corresponding queue. That is the only different thing. And the evaluation environment is actually consists of two applications. First, only simulates software components which are sending requests, and those two applications are connected with the IPC mechanism, more precisely the message queues. And basically, the request will be dispatched to corresponding queue based on software component ID, which are representing, of course. And for testing purposes, we utilize the unit semantic segmentation. We utilized unit semantic segmentation, which we can see here, YOLO object detection, and 2 Google Nets. The platform which we used for testing was Jetson Xavier, and of course, here we can see how requests are executing, and we can examine if the order is the expected. Also, we actually measure the delay introduced by this program, and it was approximately about 5 milliseconds. So basically, it will not make a big harm to these algorithms. And basically, we can conclude this paper presentation by saying that this paper presents a comprehensive problem of deterministic execution on GPU and proposes one solution for kernel scheduler as a step towards providing the required determinism as a very, very challenging job to do. We also actually present the entire algorithm, entire scheduling process, and measured some latency and some potential limits of our program. And that will be everything. Thank you. We can proceed to the questions, I believe, now.
Maybe you can a little bit mention about the assignment of the priorities, Dušan. How do you assign the priorities in this kind of an application?
Yeah, well, basically, we assigned event trigger tasks to have the fixed priority, and basically, it is something that will need to be determined completely in the process of utilization of this program, when in the moment when we can have a actual software components. So basically, the ones which are components from driving assistance services and control services will certainly have the higher priority. And if their tasks are event trigger, they will go to the priority queue. And if not, if their tasks are time constrained, they will go to EDF or EAT, basically on only depends on firstly on if it is time independent or not, and secondly if there are exact times of execution. And of course, the
5 millisecond is your promised delay, right?
yes, it's
So
about 5
anything
milliseconds.
above cannot pass it, right? Anything.
I think we don't have some wide spectrum of test cases. Maybe it will be a good something that we really need to work on a little more to see if that number will be certain for each case. But currently we measured that delay.
But let's say you have a door lock signal with 5 milliseconds delay, so it's waiting in the queue, and then you have an urgent request from some other process. What's your privilege in your system?
Well, basically that 5 milliseconds delay is something that program will take for its execution. If there are some kinds of tasks which you mentioned with the highest priority, they will probably all, based on our current research, they will all have some kind of predefined activation time. I mean, their runnable will have some kind of predefined activation time. So basically, they will always be in a EAT queue, which has the highest overall priority. They are only considered as a first one.
Okay, that makes sense.
Thank you.